This video is about ionic and metallic solids, and what we're going to do is look at how particle size and the attractions between the particles that make up a solid are going to dictate the structures of those solids. To begin, we're going to look at some basic structures of particles that are in a crystal lattice. So a crystal lattice is just a fancy way of saying how do the particles stack in a three-dimensional structure. The most simple one of these is called a simple cubic. In a simple cubic, there is one particle at each corner of a cube. So this is a view of what we call a unit cell. So this is like the simplest repeating unit in that simple cubic structure. And since the particles at the corner of this cube are sliced in half, then they're sliced in half again, then they're sliced in half again because they're sharing with neighboring cubes. That means we have 1/8 of a particle at each corner. And there are 1, 2, 3, 4, 5, 6, 7, 8 corners. So that means that the total count in a unit cell is there's one particle per cell, 8/8. The length of the edge we can calculate by thinking about the fact that this is one radius from here to here, and then there's a second radius from there to there. So one edge, one side, is 2 radii. And that's going to be the same thing, no matter which direction that you choose. So the edge length is 2 times the radius of whatever particle is in there. If it's an atom or an ion, doesn't matter. The edge length is 2 times the radius of whatever that particle is. Another kind of basic crystal lattice structure is called a face-centered cubic. This is a kind of a view of a face-centered cubic arrangement, but if we slice that like one unit cell out, we find that there's one particle at each corner of a cube and then one in the center of each face. It's a little bit hard to see this, so let's isolate that unit cell. Once again, we find that we have 1/8 of an atom, 1/8 of a particle at each corner, so that's going to make up one atom. But each face has a particle that's been sliced just in half. So at each face we have half of an atom. On a cube there are 6 faces, so that's 6 halves, which is 3 atoms. So that means the unit cell contains 4 particles, 8/8 at the corners and 1/2 at each face. Let's figure out what the edge length would be. If we look at the edge as having length S, there's S this way, and then there's S this way, and then we can make a right triangle by connecting those. And this right triangle has a radius, then 2 more radii, and then another radius. So S squared plus S squared is 4 times R squared by Pythagoras' theorem. So that means 2S squared is equal to 16 times R squared. If we divide both sides by 2, that means that S squared is 16R squared over 2. And then to find out just what S is, we find out that S would be, take the square root of both sides, 4, that's the square root of 16, R divided by the square root of 2. So 4 times the radius of the particle divided by the square root of 2, that's an edge length. Another name for the face-centered cubic that's often used is called cubic closest packing, or CCP. And it's called that because this is as close as particles can get shoved into each other in this structure. And this is actually a fairly common structure. The third one that we're going to look at is something called a body-centered cubic, or BCC. Here's the unit cell for a body-centered cubic, and when you see the unit cell, you can see why it's named that. What you have is one particle at each corner of the cube, but again, it's sliced in half, in half, and in half. So it's 1/8 of a particle at each corner, so that makes up one atom altogether. And then in the very center of the cube, so centered on the body, not centered on the face, there's another atom. So that makes a second atom. So the number of particles per cube, or unit cell, is 2. Calculating the edge length is a little bit more complicated. Let's do it by looking at an edge, call it S, and another edge. So we're going to look at the edge at the top and the top front and top right here. And then let's look at the diagonal that cuts across that top. So that diagonal is, we want to find out what that is. It's going to be s squared plus s squared. That's the diagonal squared. So 2s squared is the diagonal squared. So the diagonal is the square root of 2 times s. Now let's take that top diagonal, which has a value of square root 2 times the side length, and use that as one leg of a right triangle. The other leg, let's have that be s, which is the edge length. Now let's think about the diagonal that cuts right through the middle from this back right edge up to the top left corner. It's going through one radius here. It's going through a whole atom here, so that's 2 radii. And then it's going through another radius here. So that means that one leg squared, which is square root of 2s, that's the diagonal squared, plus s squared is equal to 4r squared by Pythagoras' theorem. So that means that 2s squared plus another s squared is equal to 16r squared. And that means that 3s squared is equal to 16r squared. So that means s squared is 16r squared divided by 3. And if we take the square root of both sides, we can finally figure out what s is. S is going to be 4r over the square root of 3. So that's our edge length. The edge has a length of 4 radii of whatever particles in there divided by the square root of 3. Now in practical terms for this class and for the AP exam, what you might be asked to do is to use the equation for edge length for one of these kinds of cells to calculate density if you know the mass of the particle, or if you know the density, you might be asked to work backwards to figure out what is the radius. In fact, that's how they figured out a lot of these radii. All kinds of substances exist in these lattice structures. We're going to look at 2 common ones. One is metallic crystal structures. So forgetting about the specifics of the geometry of the lattice, let's talk about what are the particles that are at the lattice sites. In other words, what are the particles in those unit cells? For a metallic structure, metal atom cores are the particles at the lattice site. Atom cores are the nucleus plus the electrons that are in all the shells except for the highest shell. Those are called the non-valence electrons. And the ones that are in the highest shell are called the valence electrons. The valence electrons in metals, it turns out, are free to move around. They are not restricted to stay in their atom. And so as they're mobile, moving around, they are attracted to the positively charged cores, because the cores, remember, are missing some electrons. And the attraction for these mobile electrons for all the nuclei and non-valence electrons, the atom cores, that positive-negative attraction is what holds the structure all together. And this gives metals the characteristics that they have, which is they're bendable because you can flux them around and they still stay together because of the attraction of atom cores to a moving set of particles. They conduct electrical current really well because those electrons in the middle are free to move around. Most of the properties that metals have are because of the fact that they're bonded together in this way. In pure metals, all of the atom cores are the same. Like if you have pure gold, it's all gold atom cores. If you have pure copper, it's all copper atom cores at the lattice sites. But when you mix metals together, you have what's called an alloy. And an alloy has the same basic structure except for the atom cores are just atoms of different elements. So one example of an alloy is the gold that most jewelers use. It's an alloy of gold with some other element, like lots of times it's silver. So some of the atom cores are gold, some of the atom cores are silver, but they're all held together by that attraction for their shared mobile electron C. It's often called the electron C because it's mobile. And the cores are like islands in the sea in that model. There are 2 kinds of alloys. One kind is called substitutional alloys, and the name kind of makes sense. In this case, the atoms are of similar size. They're close enough in size that one can just substitute for the other in the lattice. So an example of that would be 24 karat gold. This is an alloy of gold and silver. Gold and silver are close enough to the same size that silvers can just slip into the lattice in place of some golds and substitute for them. That's why it's called a substitutional alloy. So that's when typically they're both metals, and then also they're approximately the same size. The other kind of alloy is called an interstitial alloy. And in an interstitial alloy, the atoms are different in size enough that one of the atoms is small enough to fit in the little interstices or interstitial holes, the little gaps that are left in the lattice. An example of this would be steel. Steel is a lattice of iron atoms, but carbon atoms, which are small enough to fit in the little gaps in between the atoms inside the lattice structure, they just stick in there. And that's what makes steel steel and not just iron. Some details about interstitial holes, and this is really hard to see in a flat surface like you're looking at right now. It's much more easy to visualize this if you have a three-dimensional model to look at that you can actually move your head around and look inside. But a tetrahedral hole is a type of hole where there are 4 atoms arranged in a tetrahedron, and that leaves a hole in the center. So here we see, it's like we're looking at the top of a stack. So this atom, and this atom, they're on the bottom of a stack, and then this one here is at the top of a stack. So it's like, it makes a pyramid. It's a tetrahedron, a 4-sided figure. If I try and trace that out, these lines here go between the centers of the bottom atoms, and this goes from the center of the top atom down to the centers of each of the bottom atoms. In between there's a hole. That's the interstice, or the interstitial hole. And there's a space for a particle, if it's small enough, to fit inside there. Another type of hole is an octahedral hole, and this is where 6 atoms are arranged in an octahedron, and they leave a hole in the center. So this is like 2 stacks of 3 that are just offset by 120 degrees. If we trace this out, there are connections between the center of this atom, this one down here, and this one down there. And then those centers connected to the center of this atom down there. And then those centers are connected to this atom up there. That makes an octahedron, an 8-sided figure, and the interstitial hole is in the center of that. Now let's look at a face-centered cubic unit cell, because it's the most common one, and find out where the holes are. So there's one octahedral hole right in the middle. Here's the octahedron. There's kind of the base of it. And then there's one pyramid going up. That's 4 sides of the octahedron. And then if we connect to the face-centered atom in the bottom, there's the other 4 sides of the octahedron. Right in the middle of that octahedron, there's a hole. So there's a space for a particle to go there. There's also a hole on each edge, and this is harder to see, and you have to keep in mind that this unit cell is attached to another unit cell up on top, and another unit cell off to the side. Now, if we connect the face-centered atoms and the corner atoms, we can make another octahedron. So there's a hole on that edge. That's going to be true for all of the edges. So if we think about that hole on the edge and having an atom in there, and there's 12 edges, that makes 12 holes. There's 12 edges because there's 1, 2, 3, 4 on the top, 4 on the bottom, that makes 8, and then 4 edges around the perimeter, and that's going to make 12 edges. So these are the locations of the holes. But if you think about the fact that each of these are sliced in half at a corner and then sliced in half again, because they're shared by 2 other cells, so they have to be sliced in half, that means it only gets a quarter share of each hole that belongs to that cell. So there's 12 edges, that means 12 holes, but it only gets a quarter of each hole, so 12 divided by 4 is 3. So that means on the edges, the edge holes, the octahedral, the face-centered cubic unit cell only gets 3 of them. And then there was 1 in the center, so that leaves you a total of 4 octahedral holes per unit cell in a face-centered cubic. Let's look at tetrahedral holes. There's 1 hole in each corner. Here's our tetrahedrons. It's face-centered, 3 face-centers connected together with a corner. There's your hole. A particle can fit in there. So there's 1 hole in each corner, and there's 8 corners, and this hole is completely inside the cell, so that means you get 8 holes per unit cell. So let's summarize. In a face-centered cubic unit cell, there are 4 lattice atoms per cell. There are 4 octahedral holes per cell, a 1/4 share of 12 on the edges, and then that 1 that's in the center. There are 8 tetrahedral holes per cell, 1 in each corner, and they completely belong to that unit cell. So that means there's 1 octahedral hole per lattice atom, and it also means there are 2 tetrahedral holes per lattice atom. Ionic substances, as well as metals and alloys, fit into these ionic crystal structures. How this works is the larger ion occupies the lattice sites. Those are the particles in the lattice. Typically these are anions because the anions are usually bigger because they're gaining electrons, not losing them. The smaller ions, which are typically the cations, they occupy the interstitial sites, the holes inside of the lattice structure. Here's an example. ZnS, the zinc 2 ions are smaller than the sulfur. So the sulfur makes up the lattice, and then in the interstitial holes there are zincs. Because they're occupying half the tetrahedral sites, and there are 8 tetrahedral sites, that means there are 4 zincs in a unit cell. But the lattice has 4 sulfurs, so it's 4 sulfurs for every 4 zincs, so that means the formula is ZnS. This is what the whole thing looks like, with more atoms closely stacked. Here's another one, very common, sodium chloride. The sodium ions are smaller, and the chloride ions are much bigger, and the sodium ions then are in the interstitial sites, and they occupy all of the octahedral sites. There are 4 octahedral sites per unit cell, and there are 4 lattice sites in the unit cell as well. So there's the same number of chlorines in a unit cell as there are sodiums, so the formula is NaCl. Here's another view with them all stacked together. And if you look at it carefully, you can make out the face of a face-centered unit cell. There are the corner atoms of chlorine, and there's the face-centered atom.